In Chapter 7 in Class Problem 2, we're going to explore the capabilities of the Clapeyron equation and how we could use it to relate temperature and pressures at phase transitions. In particular, we're going to focus on the ice-water, or the water phase transitions. And so in Part A of this problem, what we're interested to look at is the ice-water phase transition. And we're told that the heat of fusion, or the enthalpy of melting, has a value of 335 kilojoules per kilogram at a temperature of 0 degrees Celsius and a pressure of 1 bar. We're also told the densities of water and ice. And what this problem wants us to do is it wants us to develop an expression that relates the melting temperature of ice with that of pressure. Okay? And so it's a fairly straightforward premise. And so in this problem, what we're going to be looking at is solid ice turning into liquid water. And our goal will be to develop an equation that relates the melting temperature to the environmental pressure. All right, and so with this sort of problem, where we want to start is we want to start with the Clapeyron equation. And so the Clapeyron equation tells us that the partial derivative of pressure with respect to temperature at a molar or a delta G value of 0, that's going to be equal to 1 over temperature times the enthalpy of the solid to liquid transition divided by the change in volume of that same transition. Since we're dealing with the melting of solid ice to liquid water, this delta H S to L, that's going to correspond to our enthalpy of melting. And for the purposes of this problem, since we're only given one value, we're just going to assume it's going to be constant over, a given temperature and pressure range that we're given. For this delta V value here, that's going to be equal to the molar volume of the liquid phase minus the molar volume of the liquid phase, minus the molar volume of the solid phase. Okay? And in terms of density, that's just going to be 1 over the density of liquid minus 1 over the density of the solid. Okay? All right. And so with that in mind, what we could do is we could, in order to solve this differential equation, we could move it to this side over here, the temperature. And what we're going to have in the bottom is a dt divided by t is equal. And so now that we have, well, actually before I do that, let's do it like this. If I move temperature over to the left-hand side, I could combine this temperature with this dt down here. Okay? All right? And mathematically, this dt over t, by definition, is also the derivative of the natural log of temperature. Okay? And so we have that is equal to delta Hm divided by molar volume of the liquid minus the molar volume of the solid. Okay? So now that we have this relationship, all we have to do is just kind of move the temperature terms to the right-hand side. And then we integrate. So we integrate the left-hand side from pressure 1 to pressure 2. These terms on the right-hand side are constant. And we're going to integrate this natural log of T from temperature 1 to temperature 2. And based on the log rules, we then end up with a natural log of T2 over T1. Okay. Now that we have this relationship, we could rearrange it to solve for T2. Okay. So just by manipulating the Clapeyron equation, we can now relate the melting temperature of our ice to the pressure. So that's part 1 of the problem, or part A. In part B of the problem, what we're going to deal with is vaporization. Specifically, we want to look at the steam-liquid-water phase transition. So we're told that the enthalpy, or the heat of vaporization for that transition, is 2255 kilojoules per kilogram, and that occurs at a temperature of 100 degrees Celsius and 1 bar. And so, similar to part A, this problem wants us to develop an expression that relates the boiling point temperature with that of pressure. Okay. All right, and so in part B of this problem, we're going to be looking at liquid water. Turning into vapor. And the goal of this part is to develop an equation that relates the boiling point temperature to the pressure, the environmental pressure. And so once again, with this type of problem, we're going to start with the Clapeyron equation. Okay. The Clapeyron equation is this again. And for our delta H, we're going to be looking at that enthalpy of vaporization. And our delta V, this time we're going to be looking at the difference between the molar volume of the vapor minus the molar volume of the liquid. And so now that we're dealing with the liquid to vapor transition, we're going to make a couple of assumptions. The first assumption we're going to make is that the molar volume of the vapor is going to be much greater than the molar volume of the liquid. And so essentially our denominator is just going to be the molar volume of the vapor. Now that we have the molar volume of the vapor in the denominator, we're now going to turn that into, we're going to apply the ideal gas law. Okay. By applying the ideal gas law, we could turn that, actually this is a specific volume, not the molar volume, so it's in kilojoules per kilogram. We could relate that to temperature, pressure. Over P. And in order to get this in terms of moles, we need to also multiply it by the molecular weight of water. Okay? Or actually, yeah, multiply it. Okay? All right. And so now that we have this equation, what I'm going to do is I'm going to rearrange things so that I have all the pressure terms on the left-hand side my constants on the right hand side, and then MW, and then also my temperature terms on the right hand side. From here, we just integrate the equation, and what we get is that the natural log of P2 over P1 is equal to negative HVAP over R molecular weight times 1 over T2 minus 1 over T1. From here, we could then just rearrange, and we get that T2 is equal to the inverse of 1 minus T1 minus R molecular weight divided by HVAP times the natural log P2 over P1. And remember, looking at the reciprocal of this. Okay, so just straightforward algebra and a little bit of calculus in order to develop the equation for part B. Now for part C, all it's asking us to do is essentially take our equations from part A and part B that we derived, and then use those to find the freezing and boiling points of water at a pressure of 84.6 kilopascal. Okay. All right. So for part C, we'll first let T1, what I'll call A, equals 0 degrees Celsius, and P1 equals 1 bar, which is equal to 1.013 e to the 5th Pascal. Right, and then for pressure 2, that's going to be equal to 84.6 kilopascal, or 8.46 e to the 4th Pascal. In any case, all we have to do for this part to find the new freezing point is we just need to take our answer from part A, and we just need to plug and chug. So here's our equation for part A. We know these pressures, we know this temperature, and we know all these values. So all we need to do is plug in. So T1's 273.15 K times the exponential of H melt and then for our molar volumes, right, I said those were equal to inverse density. Those are in units of meters cubed per kilogram. And then we have our delta P, 8.46 e to the 4th Pascal minus 1.013 e to the 5th. And a Pascal is the same thing as a joule per meter cubed. Okay. Once we plug those values in, essentially the terms inside of the exponential are going to be very small, right, and almost close to 0. And so with an exponential of 0, that gives us about 1. And so we find that our new freezing point at this reduced pressure is essentially the same as the old freezing point, 0 degrees Celsius. So we find that the freezing point of water is a very weak function of pressure. Now on the other hand, let's look at the boiling point. So if we let T1b equal 100 degrees Celsius, and the pressure is still 1.013 e to the 5th Pascal, and P2 is also still 8.46 e to the 4th Pascal. To find the new boiling point, we go to our answer for part B. And all we do is plug and chug. Okay. All right, so T2 boil is equal to 1 over 373.15 K minus 8.314 joules per mole K divided by 255 e to the 3 joules per kilogram. And I realize I put the molecular weight in the wrong spot. So here, in order to get the units to work out, since this is kilojoule per kilogram, HVAP, we want it essentially to be kilojoules per mole. So our MW should be up here. Let me fix that here. And also fix that here. In any case, our molecular weight for water we know is 18 grams per mole. In kilograms, it's going to be 18 times 10 to the negative 3 kilograms per mole. The natural log term for the pressures, 1.013 e to the 5th Pascal to the negative 1. And we find that at this reduced pressure, that our boiling point actually drops by about 5 degrees. Right. And so in Denver, Colorado, ice freezes at the same temperature, but water boils at a lower temperature.